So I had a conversation with Michelle, and I'm not sure that I completely have explained to you or that you understand the concept of gear ratios, not all of you anyway. And so I thought I'd run over this, and we'll use the actual sort of robot schematic here as opposed to something that's abstract, and see what we can if we can get a better idea. And since we'll have it recorded here, you can go back over it if you don't understand it and generate some questions. I'll be more than happy to answer. The whole concept of how fast do you want the glyph to be raised is the one that sort of started this, and I actually had you lift the block and counted off 1001, 1002, and that sort of thing, and it looked like in the very beginning, once again this is just in the beginning because we had no idea what our design parameters would be, it looked like 6 inches per second. In other words, be able to raise up the glyph high enough to put it on another glyph in 1 second would be a good place to start. Okay, so that's where we started. The other piece of information we knew is that the motor is 152 RPMs. You divide 152 RPMs by 60 seconds in a minute, and you wind up with 2.53 revolutions per second. So the motor turns 2.5 revolutions for every second, and we want the glyph to be raised initially at 6 inches per second. So let's strip away all of the other extraneous pieces there. There's only one arm I show here because the other arm is just parallel to it. So this could be the lower arm. I think I'm actually using the lower arm because I put a few dimensions in here. So let's take a look at this. And so if we look over here at the arm, and the arm is going to have to lift up such that the vertical dimension on the right is 6 inches in 1 second, and we already know that the motor is going to rotate 2.53 revolutions that second. If you look on the left hand side, the 2.53 times 360. Why 360? There's 360 degrees in 1 revolution. So the motor is going to run in 1 second, is going to rotate through 910.8 degrees. If I look at the right, I got 6 inches. Well, inches and degrees are not the same units, so what do I have to look at? The lower arm moving to the upper position, there's an angle in there called theta 3. So theta 3 is how far that has to move, how many degrees of an angle that has to move when the motor moves through 910. And so let's find out what that is. That equates to 6 inches. Well, the good news is that we actually can measure the x and the y dimensions to the end of the starting position of the arm. I think originally we had about 8 inches. See, x may be 8 inches. We've moved it back since then, and I think the y was around 10 inches. So now we have enough to define this triangle. Since it's a right triangle, we can use x squared plus y squared equals z squared, which we turn out to find out that the length of it was 12.8. I think it was around that. So let's use that. So we actually can get theta 1. And the reason why we want to get theta 1 is the angle that we're interested in, theta 3, is actually theta 2, which is the angle it moved through, minus theta 1. So how do we get theta 1? Well, you could take a protractor, a protractor, and put it on there and just measure it. Or you can use a little bit of trigonometry or geometry, and up there I put down there theta 1 is the inverse tangent, and tangent, of course, is the opposite, which is the 8, over the adjacent, which is y. On your calculator, you put inverse tangent, and you find out that angle at rest is about 38 degrees. You go to theta. Now we need to do theta 2. We move it up. We happen to know that the thing lifted 6 inches, so we can actually go across and take the 6 inches and subtract it off from the 10. So now we have a triangle which is a height 4, and of course we still have the 12.8 on the hypotenuse. In that particular case, the cosine of the angle, which is the adjacent over the hypotenuse, and we take the inverse of that. So we have 4, that's the 10 minus the 6 inches, over 12.8, and it says it's 70.52. Subtract the 2, and theta 3, voila, comes out to be 42.52 degrees that we can turn through. Once again, you could have measured it with a compass, or protractor, I'm sorry. So what's the gear ratio? Well, it's basically the 910.8 over the 42.52, and there we come out with a gear ratio of 21.42. Approximately. Could have been 22. I think we calculated 22.5 at the on the board. Okay, so how big of a pulley or gear or whatever do we need to get the 21.42, because we're basically going to rotate. That rotation of that pulley is going to be connected to that arm, and so as it rotates, so does the arm. So how big is it back? Well, we know that the little purple pulley down there is about a ½ inch in radius. You guys can actually go measure it so you could get a better idea of this. And then, so what would it take for a 21.42 with a ½ inch radius? How big do I have to get it so that at 2.53 revolutions per second I raise it 6 inches? Well, it says that we have to have a radius of 10.71. That would mean that the pulley or gear or whatever we would have to be 20 inches in diameter, which is bigger than the box that we had. So we had a little bit of a dilemma. So what we did was we had to think about this, and we had to so what we did, how did we deal with that? Well, we reduced, basically we skipped a step here in that we tried that gear thing where we made a small gear, and you know we had some troubles with there, and part of it was because we didn't have a 10-inch gear, and we were trying to do some interesting things with that. So we went to the kind of the yank pull down thing, and we were able to modulate the power. Modulation means we reduced it, we limited it down, and we were very fortunate that the torque on the motor was high enough that we could actually lift it. So we lowered the speed of the motor. That was good, and it still was able to lift it. We actually reduced the Momenar, that's the big gear, but we did make it bigger than the first test when we had the little plastic cogged one. And you can actually measure that now and take a look at it. I'm going to guess it's about 5 inches. And so you can say, well, gee, if we really have about half of what we had before, we probably are twice as fast. The answer is almost, but we did reduce the power. So between reducing the power and being able to get a little longer arm than we had before, but certainly not as long as 10, we came up with kind of a Goldilocks solution on that. So that was good. So what about all this gear ratio thing? Well, I know this sounds silly, but Archimedes actually said it very well. He said, give me a lever big enough and I can move the world. The whole concept of gear ratio is kind of like a teeter-totter. It's kind of like a lever. You got a fulcrum. You got one distance on one side, got another distance on another side, and you're trying to find out, well, how much force do I need on one side? We all know that if we had a fulcrum and we needed to move a rock, if we had a really long lever on one side, we could actually move a pretty heavy rock on the other side. Albeit, there is a trade-off that you have to move a long way for it to move a little bit. But it gets a lot of force, and you don't have to have so much. So could our little electric motor lift a Volkswagen? Well, the answer is yes. So if you make the gear ratio big enough, hence Archimedes, give me a lever big enough I can move the world, you could. We'd have to make it really, really big, and we'd obviously would have to make the other parts a lot more substantial because they would just absolutely get smashed and crushed to death. But you could eventually make something that would do that with the torque that you have. So if you ever get kind of befuddled by this, because you just saw that seemed a little bit complicated that we have, but think of a teeter-totter or a lever, and I drew a little picture there of the old teeter-totter that you got a big force on the left but a small distance for equilibrium. When on the right I have a small force and a large distance, and then of course somewhere in there, there's probably in most mechanisms there's some sort of a gear ratio. So recognizing that when you look at a teeter-totter, it looks pretty simple. When you look at what we had, it was quite a bit more complicated. Anyway, there you have it. If you have any questions, let me know. Take care.